Good morning, students. Welcome to Real Analysis live lectures. In this lecture, we'll discuss about totally bounded spaces, what is meant by a metric space when a subset is totally bounded and so on. Okay, fine. So take a subset of metric space M. A is a subset of M. Then we say that A is totally bounded if for given any epsilon greater than 0, if we can find some finitely many points from M such that A is contained in unit of balls, epsilon balls around X size. Okay, that means if this is your set A, uh, whatever epsilon you give, if we can able to find some balls, okay, such that this entire A can be covered by such epsilon balls. Okay, if we quickly recall what is meant by bounded, a set is said to be bounded if there exists one epsilon such that A is contained in that ball of epsilon radius. Okay, so you can see that this totally bounded concept is actually stronger than this boundedness because this totally bounded demands for every epsilon greater than 0 you should able to cover A with finitely many bonds. Okay, whereas boundedness it is enough if you give one one ball which contains A, right? So soon we'll see that uh, totally bounded implies bounded, but this is not true in general. But of course, one will give examples and all little later. Okay, fine. Now, so what is this epsilon x1, x2, xn if from M is called epsilon net for A. So A is said to be totally bounded if given any epsilon, if we can give a net for that, right? So that means whatever smaller radius or whatever radius we give, A should be able to cover by finitely many balls of that radius, right? These xi's are coming from F, but actually we can prove as a lemma instead of those xi's coming from M, we can make sure that they are actually coming from A. That means if A is totally bounded, then actually for given any epsilon greater than 0, we can actually find xis are you call it as yi is coming from A itself such that A is covered by union of such balls. Okay, and it is very simple. Proof is not at all difficult one. By definition, A is contained in union of bxis. This the only thing is, see this, if this is A and if at all some ball is this, okay, right, then you simply forget about this xi, no need to take this ball, right? So without loss of generality we can assume that this A is intersecting every ball we have mentioned here in this union. So A intersection B xi of epsilon by 2 radius, we assume that this is non-empty. Okay, so once this is non-empty, that means we can find an element here which is also here. So suppose something like if we write, suppose this is a ball, then what we take here is instead of taking xi is somewhere here, suppose say assume xi here. So what we'll take here is from this much part you consider any yi. Okay, if it is already xi is already inside the ball, then there is no problem. You can take anything which is there which will work. Okay, but if at all some portion of the ball is outside this A, then we are taking an element which is in the intersection. Okay, so you take yi is belongs to this, right? Then you can find using triangle inequality and so on, we can easily get this one, that A is covered by this b epsilon around yi. Okay, so if we see here what is meant by A is totally bounded, if first as a definition is that A is contained in union of balls of epsilon radius where xi belongs to M. Now as a second, just now what we proved is that A can be covered in union of byis, okay, where yi belongs to A itself. Now we show the other interesting one in terms of diameter of sets. That means we show that A is totally bounded if and only if there is given in epsilon greater than 0. So given epsilon greater than 0, there exist finitely many sets A1, A2, AN, which are subsets of A. The condition on AIs are nothing but their diameters. Each diameter is less than given epsilon, such that A is contained in union of these AIs. Okay, right? So we are giving an equivalent characterization of totally bounded, that A is totally bounded if and only if there exist fi finitely many sets whose diameter is given less than epsilon, such that A is contained in union of AIs. Okay. The proof is again not at all difficult one. By using the fact that A is totally bounded, what we know is that A is contained in union of Bxi's, okay, some radius. So here we call it as epsilon by 3. Okay, right? It is contained here. So simply take uh, so whatever the ball is, if this is Bxi, okay, epsilon by 3, and see, suppose this is your A, right? They only take this much part as your A1, right? And if some ball is already inside, then you take that its entire thing as AI, right? So what is our AIs? AIs are nothing but these balls together with A intersection. Then you can easily check that diameter of AI is, because it is inside this, so you will get less than epsilon and so on. So only idea is, from those balls you remove whichever is outside A, okay, and remaining things you collect as AIs. Then A can be written as union of AIs. A can be covered by union of AIs, and by the way we have selected AIs, the diameter is less than epsilon. We can see that. Okay, and the converse part is also same. So if A is covered by union of AIs, then we can you can check that this AIs is contained in ball around xi, because of diameter of each AI is less than epsilon. So in particular we can take here epsilon by 2 and so on. So diameter of AI is less than epsilon, so we get from this, okay, AI is contained in ball around where xi belongs to AI, okay, where xi is any point in AI, right? So therefore obviously A is contained in union of AI, so therefore is contained in union of BXIs, right? Fine. So we have reduced the totally boundedness in terms of sets whose diameter is less than epsilon. Okay, you can have some examples now. So if you take any metric space, obviously a finite set. So if M is a metric space, okay, and if A is a finite set, then A is always totally bounded. Okay, it's very obvious why. Because if A you can say x1, x2, xn, then simply take your AIs are xi's. Then because of singleton, diameter of AIs is 0, which is less than any epsilon, and A is union of AIs, right? That shows that A is totally bounded. Okay. Now we prove an important concept, result about a discrete metric space. In a discrete metric space M, a subset is totally bounded if and only if it is finite. So in a discrete metric space, we'll take, so in a discrete metric space, what we can observe here is that a set A is totally bounded if and only if A is finite set. So in a so if you have a discrete metric space and if you have an infinite set, you can immediately say that it is not totally bounded. Okay, the proof is not a difficult one. We want to show that in a discrete metric space, if at all A is totally bounded, then A is finite, and if A is finite, then it is totally bounded. One way is obvious. This is obvious, which we have just now proved. Every finite set is totally bounded, right? We want to prove the other way. Suppose assume that A is totally bounded, okay, and we want to show that in that case A is a finite set, right? Okay. So suppose if A is infinite, then we get a contradiction somewhere and so on. So suppose assume that A is totally bounded. Okay. um, Suppose assume that A is totally bounded, then for epsilon greater than any for epsilon greater than 0, so in particular you take epsilon is equal to 1, right? So clearly 1 is greater than 0. So what you know that there exists A is contained in union of balls, okay, of radius 1, right? But in a discrete metric space, what we know about B1 of xi is simply the singleton xi. So A is contained in union of xi's I is equal to 1 to n, with and this side it is a finite set. So a subset of this that shows that A is also finite. Okay. Fine. Now, as we discussed the beginning, we can see that every totally bounded subset is always bounded, but bounded is not necessarily be always totally bounded. How you can prove this one? The idea is very simple. Because it is totally bounded, so for this epsilon greater than 0, in particular you take take epsilon is equal to 1. For this epsilon is equal to 1, what we know is that A is contained in union of balls around x size of radius 1, finite many balls, right? So for this, now take say some x1 x2, you have xn's, right? So what we do is fix x1, say, then you vary xi's, then find the distance between this, okay, for I is equal to 2 3 up to m, and you take this as maximum value among these n values. Okay, so you consider that r as maximum of these distances, then we will construct a ball around x1 of this radius r, and you can easily check that A is covered in this ball. Okay, so therefore it totally bounded is always implies bounded, right? So what we in the sense what we are taking is from x1 you try to find x2 distance, x2 distance, from x1 to x3 distance, from x1 to xn, then among that find the maximum distance and construct a ball of that radius. Okay, but the converse is not true. So that means bounded does not always imply totally bounded. Okay, why? Because you take R for example and discrete metric space. Okay, in R, so that means we are taking an infinite discrete space. So we know that in a discrete metric space, some set is bounded if totally bounded if and only it is finite. Just now we have proved it, right? So you take a set which is bounded in R but infinite. Namely, if I take suppose closed interval 0 comma 1, right? Then we know that in R A is bounded, right? Because you can find a ball, this ball around 0 of radius 2 if you take, then definitely A is contained here, right? Because this is entirely R, right? Okay, but this A, which is unbounded, is not totally bounded because A is not a finite set, right? So therefore we have seen an example of uh, totally bounded but not bounded. Okay, in that case here discrete metric space, infinite discrete metric space help. Okay, fine. Now we'll give some characterization of some properties of totally bounded subsets. So for that, take a metric space and consider a sequence xn in m comma d, and take A as its range. Okay, then if our given sequence xn is Cauchy, then A is totally bounded. See, in general, if a sequence xn is Cauchy, then we prove that it is bounded, that sequence is bounded, so therefore its range set is bounded. What we are proving here is more stronger condition, that if xn is Cauchy sequence, then its range A, that set A is not only bounded, it is actually totally bounded. Okay, and some if your range set, if that A sequence of that A is totally bounded, then xn need not be Cauchy sequence, But what we can prove is that xn has a Cauchy subsequence. So this is Cauchy subsequence, right? Okay, so this is one. So take a sequence. Then if that sequence is Cauchy, then the range set A is totally bounded. And if range set is totally bounded of a sequence, then what we can prove is that there exists a subsequence which is a Cauchy sequence. Okay, proving is not at all difficult one. You take, suppose your given sequence xn is Cauchy, then for epsilon greater than, for epsilon by 2, what you get here is distance between this is always less than epsilon for all there is some stage k and so on. Okay, so what you have to do is only you have to worry before this. Okay, so simply you take a1 up to ak minus 1 are all singleton sets xi's. Okay, that means x1 x2 up to xki minus 1. Then ak onwards it takes care, so you can get diameter of each ai is less than epsilon. Okay, and a is covered by, actually a is unit of these things, right? So therefore that shows here, so it is not at all difficult one. So what ais we are considering, up to ai ak minus 1, they are all taken as singleton sets. Then ak you simply take this one, all elements ak xk plus 1, all those things you consider as one set. Okay, then you can show that diameter of ak is less than epsilon and a is unit of ais. Okay, fine. So here I is equal to 1 to k. Now, conversely, not converse, actually, it is partially converse. So, suppose second one, if A is totally bounded, then we want to construct that Xn as a Cauchy subsequence. So, this we can split into two cases. If this given sequence, this set A is finite. See, A is a actually range set, right? So, Xn n greater than or equal to 1, right? So this, it may happen that this range set is a finite set. That means if this a is finite, then you will have infinitely many values of xi's which are equal, right? So there will be xn case which are equal, otherwise it will become an infinite set, right? So you can call it some constant k, right, for infinitely many values. That itself suggests you that this is a sequence which converges and hence it is Cauchy. So there exists a Cauchy subsequence. Now assume that A is infinite. So if A is an infinite sequence, for epsilon is equal to 1, because A is totally bounded, A can be covered by union of AI's, okay, finitely many sets. Now because A is totally bound, A is infinite and it is covered by finitely many sets, at least one of them should be infinite set. So you can call it A1 as infinite set. But of course, each diameter of each ai is less than epsilon, which is 1. So you can assume that here less than 1, right? So because A is infinite set, if each ai is finite, then union of finitely many sets is finite. So that means at least one of them should be an infinite set. We, instead of we will assume one, that A1 as infinite set. Okay. Now A1 is a subset of A. Okay, right? A1 is a subset of A and A is totally bounded. So therefore you, what you get is that A1 is also totally bounded. So this is also totally bounded. Then by taking epsilon is equal to 1 by 2, this A1 is actually covered by finitely many sets whose diameter is, so you can call it, say, suppose union of this BI's, whatever. Okay, diameter of each BI is less than half. But again, applying that A1 is infinite, so therefore one of this set outside should be infinite, that we will call it as A2. This is an infinite set whose diameter is less than 1 by 2. If you keep on repeating, what we get here is that we get a decreasing sequence, okay, right, where each one is an infinite set and diameter of AK is less than 1 by k at kth stage, right? This itself suggests that you take one element from each, so you call it xnk belongs to ak, then this you can check that this xnk converges because of this diameter property, and hence we get a subsequence which is Cauchy. Okay, Fine. So how we are getting the elements is important, that getting from totally boundedness and covered by diameter of sets. That okay. The next result is, that means we can say that now we are actually giving like characterization of n a set is totally bounded if and only if every sequence in A has a Cauchy subsequence. So A is totally bounded if and only if xn, for all sequence xn in A, there exists a subsequence xnk which is Cauchy sequence. Okay. One way we already proved that if A is um, if A is totally bounded, then if you take any xn, we know if you then we know that there is a subsequence xn which is Cauchy, right? So this way we have already proved. Then what we want to prove, that suppose assume that every sequence every sequence xn in A, okay, has a Cauchy subsequence. Then we want to prove that A is totally bounded. So how we can prove that A is totally bounded? Suppose we'll prove by contradiction. Suppose A is not totally bounded. If A is not totally bounded means what? That means there exists at least one epsilon such that A is not covered by finitely many sets whose diameter is less than epsilon. Okay, so we cannot find a you can call it net, okay, with this epsilon. That means what? There exist infinitely many elements of A, right, which are not in any one of these elements, any one of these sets, right? If at all only finitely many set elements of A are outside this, then by considering finitely many sets again constructing, you can get it this, right? So there exist infinitely infinitely many elements of A which cannot be in this of the sets AIs. That means what? There exist, we can find a subsequence x and k, right, which are not in AI. So it's the diameter of AI is less than epsilon, we said, right? So they are not part of here means what? That there exists a sequence subsequence x and k such that distance between xnp comma xnq is greater than or equal to epsilon whenever p is not equal to q, because if it is less than epsilon, then these points belongs to this sets AIs, right? Is this clear? That itself shows that this x and k is not a Cauchy subsequence, which is a contradiction to the given assumption that every sequence in A has a Cauchy subsequence, which is a not true. So where it was our assumption wrong is that we have assumed it is not totally bounded, right? So these are some of the quick properties of totally boundedness. Of